The next trend that we're going to talk about on the periodic table is ionization energy. And ionization energy is the energy that is required to remove an electron from an atom. Okay, so let's look at a definition here. Ionization energy is the minimum energy in kilojoules per mole required to remove an electron from, by definition, a gaseous atom or a gaseous ion. Okay, so we are then talking about how easy is it to remove an electron from an atom or an ion. Okay, so start thinking about this, like which valence electron would be the easiest to remove, do you think, and which ones begin to be more difficult? So first, ionization energy, and we abbreviate that as I sub 1. So the first ionization energy of an atom is the minimum energy required to remove an electron from a neutral gaseous atom. And you guys, in terms of energy and the Aufbau principle, it's going to be the electron that makes that atom or element unique from the atom or element that it neighbors on the periodic table. And so I'm not talking about taking away core electrons here. So what is it that I'm talking about? Let me make a quick orbital diagram to try to clear this up. Okay, so let's say, let's make an orbital diagram for nitrogen. Okay, so we've got 1s, and we've got 2s, and then we've got the 2 p's. Okay, and so 1s2, 2s2, and then we have 2p3, is that right? Yeah, 2p3. Okay, so when we're talking about the first ionization energy, you guys, we're talking about removing that electron right there. If we're talking about oxygen, 1s, 2s, 2p, 1s2, 2s2, 2p4, 2p4. Okay, the first ionization for oxygen, what is the electron we're talking about removing here? We're not talking about removing that one because that's not the last one added. We're talking about that one right there. Okay? All right. So that makes it unique from nitrogen that it neighbors. Okay, so how much energy does it take to remove them? Oh, okay. So this is a general equation to represent ionization, first ionization. So this is any atom. That's what A means. Any atom in its gaseous phase giving up an electron or losing its electron and becoming a positively charged ion. And of course, this is always an endothermic process. Energy is absorbed, removing that electron. It takes energy to remove the electron. All right. second ionization energy, I sub 2, is the minimum energy required to remove an electron from the whatever atom it is, positive 1 ion, to produce a positive 2 charged ion. And so removing this from nitrogen or this from oxygen, that's going to be the first ionization energy. The second ionization from nitrogen, which electron is it going to take? That one. That's the second, or I should say I sub 2, and this is going to be I sub 1. That's I sub 1. What is I sub 2 for oxygen? It's going to be that one. Okay, so it goes opposite of alpha-bow, right, building down. So the most energetic electrons are the ones that are being removed first. Okay, now how do you think the ionization energy always, I2, the second ionization energy, how do you think that that always compares in any given atom to its first ionization energy? Do you think it takes more energy to remove the first electron from an atom? Or do you think it takes more energy to remove the second electron from an atom? It's going to be the second electron. Second ionization is always greater than the first because you're removing that electron from a positively charged ion. Okay, so what you have then in your positively charged ion is you have greater effective nuclear charge. And so if the nucleus is attracting the remaining electrons even more strongly, right? You have a greater effective nuclear charge with a positively charged ion than you do with the neutral atom. Okay, it's going to be more difficult to take away the second electron. So on, so on, so on. After the third electron, even more energy. Fourth, even more energy. Because as you begin to remove electrons, that nucleus is just getting, its effective charge is getting greater and greater and greater because its positive charge is being distributed to less electrons, so it's pulling on them even tighter and tighter and tighter. Okay, so this is how it goes. First ionization takes less energy than the second ionization, then the third ionization, then the fourth. So every electron that you take gets progressively more difficult to remove and takes progressively more energy to remove it. Okay, so what are the trends that we see? What are the general trends for ionization energy in the periodic table? Okay, so what you've got to keep in mind, you guys, is the greater the effective nuclear charge, the more difficult it is to pull an electron away from an atom, right? Because it's the attraction between the nucleus and the electrons that are keeping those things, you know, in, well, quote-unquote orbit around the nucleus. Okay, so the greater the effective nuclear charge, the more difficult it is to pull away an electron, so the greater the ionization energy. All right, so if we look at the periodic table and we think about what we did yesterday, what we will find is that, in general, as we go from left to right, ionization energy increases. Okay, so if we're talking about quantum level 2, lithium has the least effective nuclear charge in quantum level 2, right? So it's got less protons in its nucleus than anything else in quantum level 2 that has electrons in quantum level 2. And so this, for period 2, lithium's going to have the lowest ionization energy. And as we move across, ionization energy gets greater and greater and greater because effective nuclear charge gets greater and greater and greater as we move across. So of course the noble gases are going to be the most difficult to remove an electron from. Okay, now there's one little discrepancy here, and that is when here for oxygen, this is actually slightly lower ionization than nitrogen, believe it or not, because it's easier to remove this paired electron, believe it or not, than it is to remove this one. Okay, that's strange. And also, now what is our other trend that we're going to see? It's going to be going down. Now, what happens to effective nuclear charge as we go down a group? Effective nuclear charge gets less, 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 and less. Why is that the case? Why does the effective nuclear charge, how it affects its valence electron, why does it become less and less and less? Because these valence electrons are what? They are further away from the nucleus. So the further you get from the nucleus, your effective nuclear charge continues to go down, 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 down. So ionization energy decreases as you go down a row, a family, a group, a column, because the effective nuclear charge is getting less as you go down. Okay, so it's just the opposite of atomic radius. Okay? Ionization energy, as you go across, ionization energy increases, and as you go down column, ionization energy decreases. And it's all, you guys, because of the effective nuclear charge. And what is dictating the effective nuclear charge? The number of protons there are in the nucleus, as well as the number of core electrons, which will shield the valence from the pull of the nucleus. But we think of all those things in terms of, again, effective nuclear charge. Okay, so beryllium, 1s, and this is, all right, so it's 1s2, 2s2. Okay, so the first ionization energy is, a certain number. And the second ionization energy is going to be greater because it's already a positively charged ion, right? And so removing this one is going to take a little bit more energy than it takes to remove that first one. But now, what about this third one? Do you think it's so much more energy consuming to remove this electron? Not simply because, you know, we've already lost 2, and so we have a greater nuclear charge because of that, but also, you guys, where is that third electron coming from? Quantum level 1, closer to the nucleus. And so whenever your ionization is coming from a quantum level closer to the nucleus, the amount of energy that it takes to remove that electron is going to jump tremendously. It's going to get much, much bigger because that electron is that much closer to the nucleus, and the nuclear charge, the effective nuclear charge, is going to be so much greater. Okay, now we're really done.